what we're starting is chapter 6. Chapter 6, exponential and logarithmic functions. We're not going to talk about logarithmic functions. At this point, we're mainly going to start looking at exponential functions. And there's two main types, growth and decay. Exponential growth, the function b of x, where b is greater than 1, is going to be an exponential growth function. Whenever that b value is greater than 1, it's exponential growth. Huh? It's exponential growth, and it increases faster and faster. So if we said 5 to the x, we do have this graph here, and if we look at the x values, they're increasing by 1, but the y values is going from 1 to 5, 5 to 25, to 125, to 625, to 3,125. It's increasing at a faster and faster rate. That's why we call it exponential growth, because it is increasing exponentially. We also have exponential decay. And if we consider a decay function, the base value, that b value, is going to be between 0 and 1. Well, let me go back over here. Well, we can say 1/5. We can see it's going the opposite direction. It's going down. If we look at the y values, they're the same, but they're getting smaller at the same amount, same rate. So it's considered exponential decay. So we're going to look at these first few here, and we're going to consider them or determine whether they're exponential growth or decay, and then evaluate for when x is 2. Now, if we look at a, y equals 2 to the x. Y equals 2 to the x. Would that be exponential growth or exponential decay? It would be growth, because our base value for this here is 2. And 2 is indeed greater than 1. 2, if that b value, that base value is greater than 1, it's growth. Now it wants us to evaluate when x is 2. So we're going to replace the x value with 2. So we're saying 2 squared. Well, 2 squared is
4.
So the value of, when we evaluate it for when x is 2, for this one here, the value is 4. That's it. Let's look at b. Y equals 1/2 to the x. Would this be growth or decay? It would be decay, because our b value, this base value, is 1/2. It's between 0 and 1. So this is questions on this here. Now, if you're not sure, especially with fractions, well, 1/2, I can convert it to a decimal, which is 0.5. 0.5 is between 0 and 1. So it's decay. Now, one more time. What was the question? So 1/2 squared. Now, when we evaluate these, we can do them by hand, or because we're saying 1/2 squared, 1/2 times 1/2. And 1/2 times 1/2 is 1/4. 1/2 times 1/2, we would do it, multiply squared across. 1 times 1 is 2 times 2.
Okay, so what do we come up with?
No.
You can't square something to become more than a fraction.
No, because you're squaring the top and bottom. If there is one, I'm not able to think of it, but most likely no.
As far as our
Yeah, there's not really any case where I see squaring it and it coming out to a whole number if it was fractional. Our next one, y equals 1.3 to the x. The base is 1.3, yes. And is that greater than 1? And since it's greater than 1, it is growth. Now we want to evaluate 1.3 to the x when x is 2. Parentheses, 1.3 squared is 1.69. That's it. Question on ABA. B, y equals 1/3 to the x. Well, our base in this case is 1/3, which would be decay, because the 1/3 is less than 1. So this is decay. Now we're just going to evaluate it when x is 2. So we have 1/3 squared. And again, at this point, 1/3 squared, we can do this in a calculator. Let it do it for us. And it'll tell us that it is 1/9. 1/9. 1/9. We feel good with this so far? Yes? Okay. Any questions on any of this so far? Now this next part, 1, 2, 3, 4, we're just asking for growth or decay. One or the other. 1/9. Yeah, you're good. If you ever need me to go back a page or slow down, ask. Tell me. Tell me if you ever need to slow down, because I do not mind. I sometimes get on a roll.
That's true. I can't keep
Now, with this here, y and f of x are essentially, for all intents and purposes, are the same thing. Now, for these here, they're not asking us to evaluate. They just want us to tell us if it's growth or decay, one or the other. So y equals 4 to the x. Growth or decay? It is indeed growth, because our base of 4 is greater than 1. So it would indeed be growth. Y equals 2/3 to the x. Decay. And it would be decay because our b value, that base, 2/3, is between 0 and 1. So it's decay. Number 3, f of x equals 0.25 to the x. It is indeed decay. And the reason it's decay is because our base,
Why did it do that?
a text pin, so it will change its text, is between 0 and 1. Our last one, f of x equals 1.5 to the x. It would be growth, because our base is 1.5, and since it's greater than 1, this would indeed be growth, exponential growth. Questions on these here? Now, that's all for 6.1. Now we're going to move on to 6.2.
What? That's it?
Yeah.
We have homework over that?
Yes.
That's the easiest thing in the world. Just make it up on your paper if it's greater than 1.
It's growth.
Less than 1, 0.
Less than or equal to 1. It is decay. Now we can't, so we'll clear these out. Because if we said -2 to the x, it won't work the same as growth and decay, because it's going to act a little weird. Okay, let's look at the graph. A nice graph, yes?
What?
If we look at the y values, when x is 0, the value we get is 1. Well, that's for anything. Anything to the 0 power is 1 except for 0. When x is 1, so negative 2 to the first, we get negative 2. When x is 2, so we're talking about negative 2 squared, it's positive 4. Then negative 8, positive 16, negative 32, 64. It is. Because this is pretty much the same values, but if you notice, it's going positive, negative, positive, negative, positive, negative. That's why we can't have that base value be negative. It has to be between 0 and 1 for decay and greater than 1 for growth, because that negative throws everything out of whack.
So what would negative 2 be?
Yeah, it wouldn't fall under our exponential growth or decay functions, because it does that almost oscillation, up and down, up and down. It is getting bigger, but since it's jumping from side to side, we can't really take an exponential or an actual graph of it without it jumping around. Now, the history of mathematics is marked by the discovery of special numbers, such as pi and I. Another number is denoted as the letter E. E, natural base. The expression 1 plus 1 over x to the x approaches E as x increases, as shown in the graph. It gets closer and closer to it. We'll never get to the actual number, like we've never reached the full number of pi, but we get close to it. And the E's approximate value is this here, 2.71828182846, and it continues on. It would be the same as finding the last digit of pi.
To the office, please.
It's an irrational number, so it's a never-ending non-terminal decimal.
I wonder what calculation the kids did.
It's dealing with perimeters. We can close in on it. Now, the first thing we're going to do with E is talking about the expression itself. Now, E, even though it does have a value, we can treat it like a variable in most cases. Now, the first one we have is e to the third times e to the sixth. Well, we'll leave it for now. What would x to the third times x to the sixth be? X to the ninth, because whenever we multiply like bases, we add the exponents, yes? Well, what's e to the third times e to the sixth going to be? Yes. Even though e does have a value, for when we're multiplying it like this here, we can treat it like a variable. So b, 16e to the fifth over 4e to the fifth. Well, we can do some simplifying, yes?
Yeah.
16 over 4 is what? 4. 4 or 4 over 1. E to the fifth over e to the fourth. When we divide like bases, we subtract the exponents, yes? 5 minus 4 is almost 1. You're good. You're jumping ahead. And since it's bigger on top, it stays on top. Since it's bigger on top, it stayed on top. If it had been e to the fifth on bottom and e to the fourth on top, then it would stay on bottom.
I write the right thing to say stupid stuff.
You're good. Questions on A, B? We good with those two there? Let's look at C. So we're saying 3e to the negative 4x squared, the whole thing squared. Now, whenever we square something, we're multiplying it by itself, yes? Now, if there had been a plus in the middle, so 3 plus e to the negative 4x squared, we would actually have to do the distributive property. We'd have to multiply it by itself and write it all the way out. But since there's no plus, there's no addition or subtraction sign between our two terms, we can just square it. We're going to square both terms. When we square 3, it's just going to be 3 squared. E, we have to use something called powers of powers, because that's really what we have. E is to the negative 4x power, and then we're putting it to the second power. Whenever we take a power of a power, those powers multiply. Because what we're saying with this here is really 3e to the negative 4x squared is being multiplied by 3e to the negative 4x. Well, over here, 3 squared is 9. Here, 3 times 3 is 9. E to the negative 4x times e to the negative 4x. Whenever we multiply like bases, we add the exponents, yes? So it'd be negative 4x plus negative 4x, which is e to the negative, if we multiply, because we multiply that exponents together. So the negative 4x times 2 is negative. So we wouldn't square the exponent, we just multiply them. Powers of powers multiply. Because the negative 4x is a power, it's an exponent. Our 2 is an exponent, it's a power. So those powers of powers multiply. Because really what we're saying is e to the negative 4x times e to the negative 4x.
The negative 4x is the exponent on.
Yes.
That's what.
We have one last thing. Now, any questions before we go into the last step? We good with powers of powers being multiplied? The only other thing we can do with this, exponents can't be negative. They can be, but we can't keep them negative. To make it positive, we move it from the top to the bottom, or bottom to the top. Since e to the negative 8x is negative on top, if I move it to the bottom, it becomes positive. Yes. Questions on ABC? We good with ABC? Easy as 1, 2, 3. Well, let's look at 1, 2, 3. E to the 7th times e to the 4th would be? Take a guess. I think you have it, but you're second guessing.
Is it X?
Big old fat.
With the 7 at the top?
Big old fat 11.
Yeah, so it'd be the same as saying x to the 7th times x to the 4th, which would be? So here it would just be e to the 11th. Now we don't have to do the x's for this, for x to the 4th, x to the 7th, because I did that on the first one to show you all the similarity between the two. So since the bases are the same here, they're both e, we can add the exponents together. 7 plus 4. That's it. Yeah, it's like an x, like our variables. Now when we divide e to the 8th over e to the 5th, we subtract. So 8 minus 5 is?
4, 3.
3. 8 minus 5 is 3, yes? If it's bigger on top, it stays on top. Whichever one had the biggest exponent. Here, the biggest exponent was on top of the fraction, so it stays on top. And the last thing we need to do for this here is 24 divided by 8. 3 over 1 are just 3. So it's 3e to the 3rd. And that's it. Question on this here. Last one for this here is 10e to the negative 3x cubed to the 3rd power. Now we're going to apply that 3 to both terms. So we get this here. Now 10 cubed is, because 10 times 10 times 10. Yes. Now with our exponent with e, we multiply the powers. Negative 3x times 3 is negative 9x.
Oh.
Very good. Questions on this here?
We put 1,000 on the top. And then the bottom.
Since the e's exponent is negative, we have to move it from the top to the bottom. And its power goes from being positive, from negative to positive. And that's it.
I went that 2,000 because I did the square of 2 times 100, but I did 100 times 3.
Mhm.
100 times 10.
Yes.
So we did not do that. That's good.
Or 10 cubed, since it's just a number, calculator can do it.
Oh, I'll do it in my head.
All right. We have one last thing. Last thing we're going to look at is exponential growth and exponential decay with the base of e. Now, when the base is e is our term that has the x, that variable, attached to it as an exponent. We're not looking at the number itself, we're looking at the exponent. If the exponent is positive, no matter what it is, if it is positive, it's growth. If the exponent is positive with e, it's growth. If it is negative, it's decay. With e, it's either positive or negative in that exponent. So when it's a number, the number has to be greater than 1 for growth, between 0 and 1 decay. When it's e, if it's positive, it's growth. If it's negative, it's decay. So if we look at the first one here, y equals 3e to the x. Our exponent is positive, yes? So it has to be growth. Because 3e to the x, well, e, as we said already, is what? 2 points. Well, that number is greater than 1, yes? So it is growth. Let's look at the next one. E to the negative 0.5x. Well, the exponent is negative, yes? So it is decay. Now, again, when we had just numbers as the base, we said the number had to be between 0 and 1 for it to be decay, yes? Now, what we're looking at here is e to the negative 0.5, yes? It's less than 1. So it is decay, yes? Now, it might be, well, might be the 0.5. Let's just say negative 1. Still less than 1. So it's not so much the number, it's the fact that it's negative. Because we said when the exponent's negative, we have to move it from the numerator to the denominator, from the top to the bottom. So that e value goes from being in the top to now being on bottom. That's why it's decay. Now if we look at 4, 1/2 e to the x, what would this one be? It'd be growth, because it's not taking into account the 1/2, it's looking at the x, the exponent, and it is positive, so it is growth. All right, Caden, y equals 4e to the negative x. So the next one, what's our exponent? Is it positive or negative? For number 5. Negative, so it'd be growth or decay. It is decay.
Okay, Caden.
Because with e, if the exponent's negative, it's decay. If the exponent's positive, it's growth. Number 6. It is growth, because our exponent, 2x, is positive, so it's growth. Be ready for the next one.
Growth is happening in our brains. I'm gonna start doing this. Your turn.
Your turn.
Your turn.
No, do that.
Nope. Nope. Your turn, Justin. It helps you learn.
No, it doesn't.
Yes, it does.
I
If you do it once out loud in front of everybody, you'll never remember how that made you feel. So you always learn how to do it. Makes sense, y'all?
now one that we didn't really look at is this here, cubed root of 8e to the 12x.
Right.
So
What's that?
might be somewhere. Now, cubed root of 8. We've seen the cubed root of 8 several times this year, yes? Does anybody remember what the cubed root of 8 is?
180? No. 200.
Because 8 times
Root of 8.
cubed root of 8. 2 times itself, 3 times is 8. Now, when we had powers of powers, we multiply. So what do we think a square root or a cubed root of a power would be? What operation?
Cube root of a power.
Mm-hmm. We take cubed root. When we did powers of powers, we multiply. So this year we would 12 divided by 3. Because when we take a square root or take a radical of an exponent, we divide the root, the number inside the radical, by the exponent. And that's it. Now, problems 1 through 4, you're going to evaluate each expression for -2 and 3. So you're going to do it for 2 different numbers. So you should get 2 answers for 1 through 4. 5 through 14, all you got to determine is if it's growth or decay, one or the other. On the back, the next set of 4, I think it's 15 through 18. Don't forget your X. You're just simplifying those like we did with E. And the last set, all you're doing is growth or decay. And that's it.